As we begin looking at differential equations and their solutions, one thing we discussed is the solutions often come in a family of solutions rather than one specific solution. So the question this video is going to answer is, how do we identify a specific solution from a family of solutions? And the way we're going to go about finding these specific solutions is we're going to take a look at a list of initial values. And it turns out we are going to need one initial value per order. So if it's a first-order differential equation, we only need one initial value to identify a specific solution. But if it's a second-ordered, we need two initial values. And those twos are going to be usually an initial value at y and an initial value for y prime. And then if there's a third-order differential equation, we need three. So you'll see a y prime prime initial value, and so on. So for example, the differential equation 2y prime plus y equals 0 has a family of solutions given by y equals a constant times e to the negative x over 2. And I can make that constant equal to whatever I want, and I'll have a solution to this differential equation. We're going to first find a solution if we're given an initial value that y of 0 is equal to 8. We're talking about the solution here, not the problem. So focusing on the solution, y is equal to 8 when x is equal to 0. So we'll plug a 0 in for x and an 8 in for the y. And when we simplify this, e to the 0 power is 1. So we have c times 1, and so we know our constant is equal to 8. Therefore, our specific solution that has an initial value of 0, 8 is y equals our constant, 8, e to the negative x over 2. And they're not always that simple or straightforward. We could ask to find a solution if the initial value y of 4 is equal to 7. And we'll follow much the same strategy. 7 is equal to our constant times e to the negative 4 over 2 power. Well, that e to the negative 4 over 2 simplifies to e to the negative 2. And so to get the constant by itself, we can divide by e to the negative 2, or just multiply by e squared, and the constant is equal to 7e squared. So therefore, we can conclude our solution is the curve y equals 7e squared times e to the negative x over 2. And I might even simplify that by adding the exponents to say it's equal to 7e to the 2 minus x over 2. Or you could get a common denominator and call it 4 minus x over 2. Either way would work, but we've got now our specific solution curve that goes through the initial value of y of 4 equals 7. Let's try a second example. The second-order differential equation x prime prime plus 16x equals 0 has solutions. X is equal to a first constant times the cosine of 4t plus a second constant times the sine of 4t. And it's no accident that this second-order differential equation has two constants in it. It turns out that those numbers will always match. So a fifth-order differential equation will have 5 constants in it as we work through solving it. We're going to find a solution if x of pi over 2 is equal to -2, and x prime of pi over 2 is equal to 1. Again, it's no accident that a second-order differential equation needs 2 initial values. And those initial values generally will come at the same point, once on the regular function and once on its derivative. And if we needed a third, we'd go on to the second derivative. So from the first equation, pi over 2 comma -2, x is equal to -2, so we'll say -2 is equal to c1 cosine of 4 times pi over 2 plus c2 sine of 4 times pi over 2. And this one's going to simplify really nicely. Cosine of 4 pi over 2 is the cosine of 2 pi. The cosine of 2 pi is 1. 1 times c1 is c1. Plus c2 times the sine of 2 pi. Well, the sine of 2 pi is 0, so that goes away completely. And we end up knowing now that our first constant has to be -2. Our second point given to us is actually on the first derivative. So we actually have to calculate what the first derivative of x is, which we can do using the chain rule quickly. It's going to be -4 c1 sine of 4t plus 4 c2 cosine of 4t. And now we can plug in the point pi over 2 comma 1. X prime is equal to 1 when our time variable is pi over 2. So we have -4 c1 sine of 4 times pi over 2 plus 4 c2 cosine of 4 times pi over 2. Again, we're going to end up with 2 pi inside sine and cosine. The sine of 2 pi is 0. So we end up with 4 c2 times the cosine of 2 pi, which is 1. And dividing by 4 gives us the second constant is equal to 1/4. And so we can say then that our specific solution for these given initial values is x equals c1, which is -2, cosine of 4t, plus c2, which is 1/4, sine of 4t. And now we have the curve that satisfies the differential equation that has the given initial values for x and x prime. Now, as we're solving these, some of them solve quickly and nicely. Others are going to require systems of equations to solve for 2 variables and 2 unknowns. You might get one equation out of the blue and one equation out of the green, and then you have to solve them simultaneously. But these are all algebra skills that you have. So the best thing to do at this point is to take your turn to practice using initial values to find a specific solution from a family of solutions. Good luck as you work on the assignment.